Back in 2000, mathematicians identified 7 problems so difficult that solving even one could change human knowledge forever. Then they attached a bounty to each of them, $1 million per problem. These weren't ordinary puzzles. They were questions that the greatest mathematical minds on Earth had been struggling with for decades, some for more than a century, without answers. That was over 25 years ago. Since then, only one problem has been solved. And the man who solved it walked away from the money without taking a single dollar. The organization behind this is the Clay Mathematics Institute. Their goal was simple: draw attention to problems so deep that solving them could permanently change mathematics, physics, and computer science. These questions sit at the absolute edge of human knowledge. Some shape modern cryptography, some connect to quantum physics, others influence weather prediction, fluid dynamics, and our understanding of reality itself. And before we begin, this is just a simplified overview. Each of these problems is deep enough to deserve its own video. Problem 1. P versus NP. This is the most famous problem in computer science, and it starts with something surprisingly simple. Imagine someone hands you a completed 10,000-piece jigsaw puzzle. Checking whether it's solved correctly is easy. You just look for missing pieces or mismatched edges. But if I dump all those pieces into a box and ask you to assemble it from scratch, that's a completely different challenge. That's essentially the difference between P and NP. P represents problems computers can solve quickly. NP represents problems where computers can quickly verify a solution if one is already given. The big question is whether those two things are actually the same. If a problem is easy to check, is it also easy to solve? Most mathematicians believe the answer is no. They believe finding a solution is fundamentally harder than verifying one. And this matters far beyond mathematics. Modern encryption depends on certain problems being extremely difficult to solve. If P ever turned out to equal NP, much of today's digital security could become vulnerable overnight. Problem 2, the Riemann Hypothesis. This one is about prime numbers, the building blocks of mathematics. Primes appear almost randomly, and mathematicians have searched for patterns inside them for centuries. In 1859, Bernhard Riemann discovered a strange connection between prime numbers and a mathematical object called the zeta function. Inside that function are special points called zeros. Riemann predicted that all the important zeros lie perfectly on one specific line in the complex number plane. If he's right, it would reveal hidden order underneath the apparent randomness of prime numbers. Computers have checked trillions of cases. Every single one matches the prediction. But in mathematics, examples are never enough. A proof still doesn't exist. Problem 3. Navier-Stokes existence and smoothness. This problem is about fluid flow, water through pipes, air around airplanes, storms in the atmosphere. All of these are modeled using the Navier-Stokes equations. The equations are incredibly useful. Engineers and scientists rely on them constantly. But there's one problem. Nobody can prove the equations always behave properly. Under extreme conditions, the mathematics suggests fluids could become infinitely chaotic at a single point, something that physically shouldn't happen. So mathematicians are trying to answer a fundamental question. Do these equations always make sense? Or is there a hidden breakdown buried inside them? Problem 4. Yang-Mills existence and mass gap. This one takes us inside the atom. Quarks, the particles inside protons and neutrons, are held together by the strong nuclear force. The mathematics describing this force is called Yang-Mills theory, and experimentally, it works incredibly well. But mathematically, nobody has fully proven the theory in a rigorous way. There's also something called the mass gap, a property explaining why the strong force only acts across tiny distances. Physicists observe this constantly. Mathematicians still cannot fully prove why it happens. Problem 5. The Birch and Swinnerton-Dyer conjecture. This problem involves elliptic curves, equations that look something like this. Y squared equals x cubed plus ax plus b. These curves are extremely important in modern cryptography. The question sounds simple. How many rational solutions does a curve like this have? Some have none, some have infinitely many. Mathematicians Brian Birch and Peter Swinnerton-Dyer proposed that the answer could be predicted using another function connected to the curve. Thousands of examples support the idea, but nobody has proven it in general. Problem 6. The Hodge Conjecture. This is probably the most abstract problem on the list. It deals with incredibly complicated geometric spaces existing in dimensions far beyond anything humans can visualize. The conjecture suggests these complex structures can always be broken down into simpler geometric building blocks. On the surface, the idea feels obvious, but proving it has defeated mathematicians for decades. And finally, the only Millennium problem that has actually been solved. Problem 7. The Poincaré Conjecture. In 1904, Henri Poincaré asked a question about three-dimensional shapes. Imagine stretching a rubber band around different objects. On a smooth ball, the rubber band can always slide freely and shrink down to a single tiny point without tearing. But on a donut-shaped object, something different happens. If the rubber band wraps around the hole, it gets trapped. No matter how much you tighten it, the hole prevents it from shrinking completely. Poincaré wondered, if every possible loop on a shape can always shrink down to a point, does that guarantee the shape is fundamentally sphere-like? For nearly a century, nobody could prove it. Then, in 2002, a Russian mathematician named Grigory Perelman quietly uploaded a proof online. Years later, the proof was confirmed to be correct. Perelman was offered the Fields Medal, the highest honor in mathematics. He refused it. Then the Clay Mathematics Institute offered him the $1 Million prize. He refused that too. He believed another mathematician, Richard S. Hamilton, deserved equal recognition for the foundational work leading to the proof. So, Perelman walked away from the money, the awards, and almost entirely from public life. He solved one of the greatest mathematical problems in human history, and then simply disappeared. 6 Millennium problems still remain unsolved, and some mathematicians believe solving them may require entirely new branches of mathematics that don't even exist yet.